Okay. Is it fine now, guys? Are you able to hear me properly?
Yes, sir.
Oh, okay. I by mistake ended the call. Right. Anyways, just let me share my screen.
Sir.
Yeah, tell me.
Sir, in the eighth question, sir, like
Mhm.
can we say in SN1 reaction, carbocation is formed, right?
Yeah.
Sir, so if in our structure carbocation is formed, then it is
Hmm.
stabilized, like it is uh, stabilized more compared to Q structure, right?
Compared to Q structure, no, Kana. It is actually stabilized in Q only more, right? Because there is one alpha hydrogen, so we will go for hyperconjugation. We will stabilize this, right? Because R, as I said here, this one doesn't have any alpha hydrogen. This one is not having any alpha hydrogen. 3 methyl groups are only there.
Sir,
Yeah.
sir, actually, according to Suprajit, like I'm adding to him. So in the R structure, if carbocation formed and then three CH3 group are there, right? So it will have more number of hydrogen is there. So it will be like one hydrogen will be escaping out and that bond will neutralize this positive charge.
Exactly. That is possible only from alpha position. Now this carbon atom, this CH3 which you're telling here, this is beta. From beta, hydrogens cannot come. Only from alpha, hydrogen can come. Are you able to understand? Even though there are more methyl groups there, you understand that
Sir.
this would have been the carbocation and this would have been the alpha carbon. Right? Yeah, tell me, Suprajit.
Sir, but like CH3 is also electron donating group, right? Like it will give electron to
Or like that
neutralize.
way. That way. Electron donating group, yes, that makes sense. Right. So if I consider the electron donating nature of these three CH3 groups, then I'll say that definitely the negative charge, positive charge will decrease. Yeah, only hyperconjugation having only one structure doesn't make sense. Yeah, actually we can change the answer. The answer would be better to go for SRQP only. But if I have to speak in terms of plus I effect, yes, that makes sense. Definitely. Okay. Right.
Okay.
Okay. Right. Next, which is the correct increasing order of boiling points of the following compounds? Now we have one iodobutane, one bromobutane, one chlorobutane, and butane. Now it's very simple. Molecular mass, greater molecular mass, more is the boiling point. More is the BP. Right? So obviously one iodobutane first, and then one bromo, then chloro, then butane. That's it. A will be the answer. No doubt about it. Next. Which of the following is correct? Now you are going for this particular case and we are going for LiAlH4 and H2O, right? Now, you understand this is an amide. Please understand this. This part, N, C double bond O is an amide. Okay. Now this LiAlH4 will convert that into an amine. Now, I don't know whether you know this reaction or not. RC double bond O NH2 if I have, and if I go for any reducing agent, that is going to become RCH2 NH2. Right, this C double bond will be reduced to CH2, and this is a very strong reducing agent LiAlH4, right? So we can easily conclude that. Okay, and we are going for hydrolysis. Nothing will happen in hydrolysis. That's it. C will be the answer for this question, right? This double bond becomes H2 and H2. That's it. C will be the answer. Okay, right? Next.
Sir.
Yes.
Sir, why can't B come, sir?
Why can't?
B, option B.
Okay, maybe if I just go by the mechanism, we'll check what is happening. So this is your thing. So here I have a nitrogen and then this, right? I mean, sorry, there is a bond and then this. Okay, now we have a double bond O and your double bond O. So from your LiLH4, H minus comes an attack here and this bond breaks. And if I do that, you will get phenyl ring with N like this, like this, like this, like this. We have one OH and we have H. Basically, this O minus takes up the H plus from water. Okay, and we have OH and H. Right now, if I have to go for hydrolysis of this, now what will happen? I will just break this bond. I will just break this bond, put H, H, OH, OH. Right? So okay, if I just start about this carbon atom, if I just trace along this particular path, there are 4, right? And then this carbon atom is having 2 OH groups and a H. And this carbon atom is having 2 OH groups and a H. And we know 2 OH on the same carbon atom is unstable. So we'll remove an H2O. So it is actually going to become CHO, 1 carbon atom. That is CH2, another carbon atom CH2, and another CHO. Same thing will happen in this also. So in that position, obviously, B will be the answer. Okay, now what? I hope you're able to understand what I'm trying to say. I'll make a page and explain again. Okay, what is the issue? Why is it? Why am I not? Okay. Okay, guys. So here we have a phenyl ring. We have nitrogen, 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 nitrogen like this. And then we have one double bond over here, another double bond over here. Now from your LiAlH4, H minus is going to attack this carbon and this bond is going to break. Same H minus will attack here and one of the bonds breaks, right? And one of the bonds breaks where you form O minus and O minus also. And that will take up H plus from water. Okay, so eventually the structure which is going to, how is it going to look is, now you have one OH and one H, sorry, one OH and one H. Same way another OH and another H. Okay, now I'm going for hydrolysis, I'm adding water. Okay, so how will you break the bond? Here you will get H and here you will get OH and here again OH and H, right? So now what is remaining here? PH, NH2 is what is coming, right? Okay, and you see that if I start from this carbon atom to this carbon atom, this carbon atom to this carbon atom, we are going to have OH, OH, and one H. Same way here, OH, OH, and a H. Now we'll remove one water molecule because geminal diols are unstable. Same like this. So can I say this is what you will have, and double bond O will be there, and one H will be there, and one H will be there. Okay, so the product should be benzene ring, that is phenyl ring with one NH2, and this particular compound CHO, CH2, CH2, CHO should be there. Where is it? We are getting OH and OH. That's not the case. We should get CHO, CHO. But now here you see NH2 is coming. Yes, D will be the absolute answer, not the C. Yes. Okay. Mechanism, all you have to understand is LiLH4 is going to give me H minus. Hydride, right? Lithium aluminum hydride, this H minus it will give. Okay. Next, this one is what is called as, this is going to be sulfonyllic acid. No, anthranilic acid. Sulfonyllic acid is going to be what? Sulfonyllic acid is going to look like this. SO3H with your NH2. This is your sulfonyllic acid. Right? So obviously the answer would be anthranilic acid would be the answer for this question. Right? This compound is what is called as your anthranilic acid. Okay, next. The IUPAC name of this compound is, okay. Now guys, okay. Fine, now what you understand is, you have COOH, COOH, and COOH in this like this, right? Now, however you try to, name it, right? You will actually miss at least one of them in the longest possible chain. One COOH you will miss in the longest possible chain, right? So in that case, what we will do, right? What we will do is, we will assume that these three are not part of the chain, right? So we'll count the number of carbon in the longest possible chain. So 1, 2, this is 1, 2, 3, 4, 5, 6, 7. Okay. Then tricarboxylic acid should come. Okay, that is not coming. So then we are able to take this and this in the main chain. 1, 2, 3, 4, 5, 6, 7, 8. We have 8. And in the fourth position, we have carboxymethyl. And in the second and the seventh, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And 1,8 dioic acid. 4-methyl ethanoic octane, and all this is wrong. Yeah, the best answer I can choose is this A. How will I tell you? So now you take this as the main chain, whatever I'm drawing here. Okay. Now, if you take this as the main chain, it will become 8 carbon atoms with wide octane 1,8 dioic acid will become, right? And you see that this is 1, this is 2, this becomes your methyl group, right? So it's 2-methyl, right? Octane dioic acid. Now in the fourth position, which what are you seeing here? This group is there. That is CH2COOH is there. This one is completely out of syllabus for you. I don't know why they're giving. Right. Anyways, whenever you have this kind of substituents, we call them as carboxymethyl. Right? Because this group will be called as carboxy group, and you have one more carbon atom attached to it, so it will become carboxymethyl. Right. So answer A will be the perfect answer for this. Right. This is out of syllabus. Okay, but still it's fine. Right. Next. Iodoform test is not given by, now you know what we need to have. We need to have this C double bond O CH3 group present in order for it to give iodoform test. Pentan 2-one. This is what is pentan 2-one. Yes, it is having the C double bond O CH3. Right? Pentan 3-one will not have because C double bond O will go here, will not have. Ethanol CH3 CH2OH. Now you can have, even you understand that this will also give your iodoform test. Why? Because when I oxidize this, this will become CH3CHO. Right? Now again, you see that C double bond O H and this group is there. So ethanol can also give. Ethanoic acid. Ethanoic acid also, what you understand is CH3 C double bond O OH. Again, you see that CH3 C double bond O group is there. Right? Only pentan 3-one doesn't have, so that will not give iodoform test. Okay, right. Next, moving on. The water pouch of instant cold pack for treating athletic injuries breaks when squeezed, and NH4NO3 dissolves, lowering the temperature. The addition of non-volatile solvent results in the depression of the freezing point of the solvent. The water pouch of the instant cold pack. Okay, and I don't know whether you have seen it. Right, there will be something like this, right, and then they crush it. Right, breaks when squeezed. And NH4NO3 dissolves in lowering the temperature. Yeah, that's true. So now once you're going to dissolve it, once you're going to press it, what is going to happen? This NH4NO3 is going to go inside the water. Right? Once it is going to go inside the water, what is going to happen? The freezing point depression is going to happen. The TF is going to decrease. Right? And obviously that's why we are doing it also. Right? To make sure that it is going to stay as ice for a long amount of time. That's why we do this. Okay. So both assertion A are true and R is the correct explanation of A. Will be the correct answer for this. A will be the correct answer. Okay, right. Next, according to the transition state theory, that is, this is nothing but your coming from. Okay, we'll see the formation of activated complex. One of the vibrational degrees of freedom is connected to translational degrees of freedom. The energy of the activated complex is higher than that of reactant molecules. Okay, the formation of one of the vibrational degrees of freedom is converted into a translational degree of freedom. No, this is wrong. First one is wrong. Right? Whereas this is okay. The energy of the activated complex is higher than that of reactants because you have seen how the graph looks. This will be the activated complex, this will be the reactant. This is having higher energy. Right? So basically A is false, but R is true. Yes. D will be the answer. Okay. Next. Alkyl halides are soluble in water. Okay. Alkyl halides are insoluble in water. Why? Now we know the mantra. Like dissolves like. Right? If I have polar solution, dissolve only non-polar solvents. Non-polar solution dissolve only non-polar solvents. Okay, fine. The attraction between the alkyl halide and water is weaker and cannot overcome the force of attraction between the alkyl halide and also that of water molecules. Now we know that, right? So when the cohesive forces must be greater than the, cohesive forces must be lesser than the adhesive forces. In the sense, when I say adhesive force, it will be in two different states. Solute with solvent is what is called as your adhesive force. Your solute with solute or your solvent with solvent is going to be called as adhesive force. So obviously this should be greater. That is, the adhesive force must be stronger in order for it to nicely dissolve. Right? So obviously this looks okay. That's what they're trying to say. The force of attraction between the alkyl halide and the water is weaker and cannot overcome the force of attraction between the alkyl halide, also that of water and water. That makes sense, right? Alkyl halides are non-polar compounds. We cannot say they are not exactly non-polar because they'll still have some net dipole moment. The moment they have net dipole moment, they'll become polar. Okay, this cannot be true. Weak hydrogen bonds exist between water molecules. No, this is not the correct. High energy is released when new attractions are set up between the haloalkane and the water molecules. No, if at all high energy released, that means stronger bonds are there. That is not the case, right? The best answer for this would be A. Right. Moving on. Isobutanol does not give iodoform test. What is isobutanol? CH3, CH, CH3, CH3. This is what is called as your isobutanol, right? Now, this doesn't have your NEC double bond of CH3 is not there, right? It doesn't have alpha hydrogen. No, that is not the case. It does not have a C double bond of CH3. That's why it is not given, right? So R, I mean, A is true, but R is false, right? Oh, moving on. Define the term Van 't Hoff factor. Okay, now Van 't Hoff factor, you will define it as the correction factor whenever, or fine. We'll just use the direct definition. Van 't Hoff factor is the ratio of the observed molecular mass by the calculated molecular mass or the theoretical molecular mass. Right, that way we can define, or in terms of calculated colligative property by observed colligative property, that also you can write. Basically, what you have to understand is, for example, when I write delta TF is equal to I into KF into M, this is your calculated value. This will put KF value, will put molarity value, you'll calculate it. Right? This you can directly measure with thermometer. So this is your observed or experimentally observed value. Right? So what is I now? Delta TF divided by KF into M. Right? That is nothing but your observed value divided by the calculated value. Right? It is observed by calculated. Okay.
Sir?
Yeah.
Sir, in terms of abnormal and normal molar mass, you define it?
Abnormal molar mass by normal molar mass.
Okay.
Right? In the same way, you can write Van 't Hoff factor I as abnormal mass divided by expected, whatever you expect. Expected molecular mass. For NaCl, it will be 58.5, the expected value. Okay. Right. Next. Calculate the volume of water which could be added to 20 ml of 0.65 HCl to dilute it to 0.2 m. Now, what you understand is, whenever you go for dilution, the solute amount will not change. The number of moles of HCl won't change. Right. So what I understand is, the number of moles of HCl from the first, before dilution, if I calculate, that will be molarity into the volume. Is it not? So 20 into 0.65 into 10 to the power minus 3. Why 10 to the power minus 3? Because it's an ml. So it'll be 10 to the power minus 3. It's mole per liter. Right? This is the number of moles we have. Right? Now I want the new molarity is equal to 0.2. That's what is happening. Number of moles will not change. That is 20 into 0.65 into 10 to the power minus 3 divided by the volume of water which should be added. Already I had 20 ml. Right? Now how much more I should add? Some X I should add. Right? And this whole thing into 1000, 10 to the power 3. So 10 to the power 3, 10 to the power minus 3 gets cancelled. Right? So can I write, I'll just make a page.
Sir. Sir, but why can't we say M1 V1 equal to M2 V2?
No, the M1 V1 M2 V2 we can say, right? But you have to understand that you should write V1 as 20, V2 as 20 plus X. You cannot directly write X. They're asking how much more volume you should add of water so that it becomes 0.2. Already 20 is there. New volume is 20 plus X. Then you can apply that. Yes, you can apply that.
Okay, sir.
Okay. Or same way you can do this. The same logic only. Okay. So now if I can just add a page. Right. So you have 0.2 is equal to 20 into 0.65 into 10 to the power 3 is gone, and divided by 20 plus X. So you get 0.2 into 20 will become 4 plus 0.2X is equal to 20 into 0.65. 2 into 0.65 or 6.5 into 2. If I do 6.5 into 2 will become 13. Right. So 0.2X equal to 9. So X will be equal to 0.45. Sorry, 4.5. Right. So I have to add more 4.5 ml of water for it to go to 0.2 2. Okay. So what should be the answer of this? Oh, it's not. It's a distinct question. So you should add 4 more ml. Right? 4 ml more you should add so that it becomes 0.2. Very easy. Sorry, 4.5. 4.5 ml. Yes. You have to add. Right. Next. An electrophilic substitution of arenes with chlorine and bromine produces ortho and para products of aryl halide. Based on what property they can be separated? Now they're asking that if
Sir.
Tell me.
Sir, previous question, it should be 45 now, sir.
Oh, yeah. 9 divided by 0.2, not 2, 45. Absolutely. 45 ml. You have to add more 45 ml to the existing case. Okay. Right. So next, electrophilic of arenes with chlorine and bromine also produces ortho and para products and how they can be separated. Now, if I have ortho, for example, if I have say OH and if I go for chlorination, I get this thing here, and I say I have OH, and I get Br here. For example, Br here, chlorine here, ortho and para product. Either chlorine or bromine doesn't matter. Right? With chlorine and bromine produce ortho and para isomers of the aryl halide. Based on what property they can be separated. Okay. Right? Now you see that para is always going to have more melting point when compared to ortho.
Sir?
And even the boiling point also.
Sir, here, how did OH come?
No, I'm just telling some random thing. Right? Any arene I'm taking, this is your ortho product, this is your para product. Is it not? And always para product will have more melting point when compared to the ortho product. So based on this property, you can separate it. Ortho products will have lesser boiling point or melting point, and your para products will have higher melting point or boiling point. That's what you write for this. Okay. Right. Next. Which of the following products will be a major product in the given below? Okay. Now we are going for this with HI and obviously going for Markovnikov's addition. So I should come here. That is what is major. So I coming here, this is minor, and this would be major. Markovnikov's addition. Very simple. Right? Explain. Again, I can explain Markovnikov's. Actually, you can look at the, what is your mechanism? It's again going to be based on stability of carbocation. First, the H plus attacks. Right? If the H plus attacks here only, we'll get the positive charge here. So if I'm a secondary carbocation that is more stable, so the I minus will come and attack here only. But if at all the H plus attacked here, the carbocation would have been formed here and I attacks here. That's a primary carbocation. That way also you can write. Or you can just write Markovnikov's rule. Okay. Right. Next. Thermodynamic feasibility of reaction alone cannot decide the rate of the reaction. Explain with the help of one example. Right. So, for example, we say that graphite to diamond is thermodynamically okay. Right? But now that means graphite, if I just keep it and I should be able to get diamond and everybody will be able to do this, right? But for this reaction to get completed, I require thousands of years. Okay, that's why we say that's why the thermodynamic feasibility, that means saying thermodynamically this reaction is feasible cannot decide the rate of the reaction, because thermodynamically feasibility we talk only about in terms of stability, right? Whereas your rate of the reaction depends on the mechanism, other stuffs, right? How the orientation looks, collision theory. You can remember collision theory. How is the rate of reaction dependent on, right? So this is a very good example. Thermodynamically graphite to diamond is possible, but whereas by kinetically, it is not possible. It is going to take so much amount of time to complete it. Okay. Right. Next. Right. Reaction is a second order with respect to a reactant. How is the rate affected if the concentration of the reactant is reduced to half? What is unit of rate constant? I know unit of rate constant will be liter per mole per second. I think I asked you to remember our formula. Mole power 1 minus n. Liter power n minus 1 per second, where n is the order of the reaction. Now you put n is equal to 2, 2 minus 1, 1, 1 minus 2 minus 1 per second. Right? Anyways, so now we have R is equal to K into A power 2. Order is 2. K is not going to change. Now we'll write as R1 and we'll write R2. Now in this case, we are making the concentration by half. So it is going to become 1 by 2 into A power 2. right? So now if I divide these two equations, then this divided by this, so I'll get R2 by R1 will be equal to KK gets cancelled, A power 2 gets cancelled. So all that I have is 1 by 2 power 2. That will become 1 divided by 4, right? So what is asking? How is the rate getting affected? Now what is happening? Now you see that R2 is equal to 1 by 4 R1. That means initially whatever I had, the final rate is 1 by 4 of that. Right? You have to write that. What is happening to this thing? It is becoming 1 by 4th of the initial rate. Ri. 1 by 4th of Ri is what is given. Like that only you should answer. Okay, very simple. Next. Formic acid reduces tolerance reagent. Why? Now we know generally only aldehydes will give, right? But your formic acid is going to be looking like this. HCHO. Now you see that it is still having CHO group present in it. Right? Well, that is one way of explaining. Or another way of explaining is HCHO is going to react with your toluenes. Right? And I know this is a mild oxidizing agent. Right? Now in that process, this is going to get oxidized to CO2 and you still form your silver mirror. This AG mirror will be formed, and that is the reason why it is, giving your tolerance test. It is because this can be easily oxidized to your CO2. Same thing happens with your other, HCOOH, right? Sorry, it's not HCHO, HCOOH. Okay, if it was HCHO, right, I would have oxidized it to form HCOOH. If it was CH3CHO, I would have oxidized it to form CH3COOH, right? But CH3COOH cannot give, because CH3COOH cannot be oxidized to give CO2. It's not that easily oxidizable. Whereas HCOOH is easily oxidizable to give CO2. That's why formic acid alone will give tolerance test, no other acid will give. Okay, right. Next, moving on. A solution of glucose and water is labeled as 10% by wheat. What is the molality of the solution? It's very simple. Now you have to understand the definition of this. Now, when I say 10%, what do you mean? 10 grams of glucose is present in 100 grams of the solution. That's why out of the total 100 grams, 10 grams is glucose. That's what I understand by 10% by weight. Now you can easily calculate the molality. Molality small m will be equal to number of moles of glucose divided by the mass of solvent into 1000. Now, number of moles of glucose can calculate 10 divided by 180 will be the number of moles. So 10 divided by 180 divided by the molecular mass, divided by the mass of solvent. This is mass of solvent, right? That is how much. If 10 grams is glucose and 100 grams is solution, can I say 90 grams is only water? Right? So obviously this divided by 90 and overall I have to put 1000, right? So now if you calculate this, okay, it's going to be 0.617, right? The answer for this would be 0.617 m. The answer, smaller. I would write the units also. Please be understand. Either you can write 0.617 m or you can write 0.617 mole per kg. You should write the units. Okay, right. Next one. Define rate of the reaction. Nothing. The rate of the reaction is nothing but the rate at which, or it is the change in concentration.
Sir, it is
divided
rate
by
constant.
What kana? Oh, define the rate of the reaction they're asking. Right? So the rate is nothing but how fast the change in concentration happening with respect to change in time. Or it is nothing but rate of change of concentration of the reactants or rate of change of concentration of the products. Right? That is how you define a rate. Oh, they're asking about rate constant. Okay, that's very easy, right? So we have R is equal to Ka power something, right? Some say some A power 1. So what you can understand is whatever is the rate when the concentration is 1m, right? We can write that rate constant is the rate when the concentration is 1m. That's it. That's how you define it. Okay, fine. The first order reaction takes 40 minutes for 30% decomposition. Calculate the T half. Now you have K value first we need to calculate. That is 2.303 divided by 40 minutes into log of 30% over. So initially I would have had 100. Now finally what I have had only 70, right? So we have 100 by 70. We have to calculate this. So K value would be how much? So we have log of.
Sir, we can do log 10, that is 1 minus log 7.
Yeah, I don't know what I can do, but anyways, you can use the logbook to find this value. This is 1.54. So this value into 2.303 equal to divided by 40. So my rate constant is 0.664. I mean 0.00664 is what is the rate constant value, right? I have to calculate T half. That would be T half will be equal to 0.69. Take another page. Okay, T half will be equal to 0.693 divided by K. So 0.693 divided by how much? 0.0064. So 0.693 divided by 0.0664. Now you have 10.43. 10.43 minutes. Yeah, everything is uploaded in terms of minutes. So answer also given in terms of minutes. 10.43 minutes is what you get as the T. Okay, right. Moving on. Discuss the mechanism of SN1 reaction. I think you know it, right? I don't have to tell you. So if I have something like this, say Cl is there. First step is this leaving, and then this carbon forms a carbocation, and that becomes the nucleophile attack, and then that will become N and C, I mean not C, another two groups. That's it. This is the mechanism. First, you show the formation of carbocation, and the second step is nucleophilic attack. Okay, and you can tell that if the chiral center, if this is going to be a chiral center, then what is going to happen? Now, once the carbocation is going to attack from the same side or from the back side, right? So eventually, if it is chiral center, all you are going to get is a racemic mixture. Because equal that side, if it attacks on the front side, one enantiomer, other side and the other enantiomer, equal probability. So 50% of enantiomers, so you get racemic mixture. That also you can tell. Okay, right. Next. What happens when propene is treated with HBr in the presence of peroxide? We know what is propene, CH3, CH double bond, CH2 in the presence of HBr, in the presence of peroxide, and anti-Markovnikov addition will happen. CH3, CH2, CH2, Br. That's what you will get, right? Benzene is treated with methyl chloride in the presence of AlCl3. Now this is your aromatic substitution, aromatic electrophilic substitution. So we have CH3Cl and AlCl3. Now I know what is going to happen. This Cl will be attacked by this to form AlCl4 minus. In that process, we'll be producing CH3 plus electrophile attacks, and then get substituted. Here we'll get one CH3. Toluene is what you get. Okay, very simple. Next. Write the reaction involved in the Clemenson's reagent. Now we know what happens in Clemenson. R C double bond O, if I have, right? So R C double bond O R or R C double bond O H, whatever in general you can write C double bond O with two more bonds. Clemenson reduction is what? Zinc amalgam in the presence of HCl. Zinc amalgam in the presence of HCl. Now you'll get CH2 and two more bonds. And Canny zero, we know what happens. We'll take, for example, benzaldehyde, and we write dilute NaOH. I know it is a auto redox reaction, right? It's a disproportionation. So one of the molecule will get oxidized, COO minus, and the other will get reduced. So that will form CH2OH. Very simple, right? Okay, next. Read the passage. SN1 depending upon blah 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 blah. I don't talk about anything here. Okay. Virtual,
previous.
yeah. Okay, don't connect this and this. This and this are different. Okay, this is the entire different molecule. Okay.
Yes, sir. Sir, here the Canisero product, can you?
This is going to get oxidized. That is going to form COOH. Right? It should have been COOH, but you have NaOH, right? So what you will have in solution is COO minus Na plus, because the acid and base will react. Right? And eventually the reduced product is going to form what? Aldehydes are reduced to what? Alcohols, oxidized to acids, but that acid will not be there, the salt will be there. That's the only difference.
Yes, sir.
Understood? Okay. And I don't have to worry about the entire paragraph, doesn't matter to me. Okay, which of the following is more reactive towards nucleophilic substitution reaction? For what? SN1, SN2? Really? Neighboring group participation? Least reactive. Okay. Anyways, I can neglect all of them and just write this as the answer. Why is it like this? Now we know that benzene ring substituents will never ever undergo nucleophilic substitution. I know we have various reasons. Double bond character, this is sp2 hybridized
sir.
carbon. Yes.
It's most reactive mostly.
Oh, they're asking about most reactive. Okay, okay. If it is most reactives, the answer would be C. But how will I tell you whether it's C? How it's going to be neighboring group participation? But neighboring group participation is not in the syllabus. Okay, guys, this is not going to be in the syllabus, but I'll still tell you. Okay, so whenever you have this double bond in the allylic position, say for example, let me make a page. Say we have this Cl, we have one CH2, and we have this double bond. Okay, so what can happen is that this double bond will be able to participate in the nucleophilic substitution reaction. How it will participate, let me tell you. This double bond can shift here and this Cl minus leaves. Okay, so when the nucleophile is attacking, this molecule, this Cl can be very easily removed when this C double bond C shifts here and this goes here. Even in case of SN2 as well as in SN1. Now in SN2, obviously this double bond will do it. Even in SN1, if this goes here and this comes out, you see that you will have a positive charge here, right? And that positive again is stabilized by this double bond, right? So allylic halides are very reactive towards both SN1 as well as SN2. Both it will be reactive. Double bond will be able to go for neighboring group participation. We call it as NGP. Neighboring group participation in involving nucleophilic substitution. And even if you check in terms of your Cl minus leaving and forming a carbocation, again, this double bond will be able to shift and stabilize this, positive charge, right? So allylic halides are generally the most reactive towards both SN1 as well as SN2. If they give you questions like this, they didn't mention anything. They just talk about nucleophilic substitution. That's it, right? Answer would be then B. Sorry, C. That is an allylic halide. Okay, right. Next. Isopropyl chloride undergoes hydrolysis. Isopropyl chloride is going to look like this. This is what is isopropyl chloride. Okay, so isopropyl chloride, it can be primary. This will be a primary, secondary carbocation, and it is secondary also. So it can either undergo SN1 as well as SN2. So definitely SN1 and SN2 both. Right. Next, the most reactive nucleophile among the following is. Now you understand that if you have CH3O minus, this amount of negative charge increase, and if it is C6H5O minus, this negative charge decreases because of resonance. O minus is there, this is C6H5, right? And when you have CH3 twice CHO minus, now double time increase will happen, and in this case, triple times increase will happen. Okay, that is one factor to consider. Another factor to consider is the bulkiness, right? But bulkiness plays a major role here because we know in SN2 or SN1, bulkiness plays a major role. Right, so even though it is increasing, all the cases increasing, but the least bulkium of the bond is this. This is the answer. Let's CH3O minus because all others are having 3 methyl groups, 2 methyl groups. This is having only 1 methyl group. So the most reactive nucleophile would be A. Right, the least bulky. Okay, right. Next. Tertiary alkyl halides are practically inert to SN2 mechanism, obviously because of what? Steric hindrance. Right? In SN2, what we have to check for is the crowdedness. Steric hindrance. So first, yeah, tell me.
Sir, in the before question, can you show? Sir, in the most reactive nucleophile, you are comparing with SN1 or SN2, sir?
Doesn't matter. So in the case of your SN1, your strength of the nucleophile doesn't matter. Strength of the nucleophile does not matter. Only in SN2 it matters. Okay. Now, why, if you ask me, now if you write the rate law for this, this will be equal to R into K into the concentration of substrate, the alkyl halide. Rx is what will substitute for SN1. And for this, you will write R will be equal to K into the Rx value into the nucleophilic concentration also will substitute. So the rate is here dependent on the nucleophile. Here in SN1, it is independent of the nucleophile. Right? So whatever the nucleophile is in case of SN1, it really doesn't matter. But in SN2, it matters. What nucleophile will have, how much strength it has, how much concentration it has, everything matters for SN2, whereas for SN1, it doesn't matter.
Sir,
Yeah.
sir, for this question, why is C6H5O minus not the correct answer?
Okay. Now we talk about this double bond is there, and we have O minus. Right. So now you understand that more and more will be the negative charge, more and more will be the reactivity, because more and more negative charge, more and more will be the love for the positive center. Right. But what
Yes,
is
sir.
happening to the negative charge? Now you understand that when this negative charge involves in resonance, this negative charge is not anymore on the oxygen atom. Is it not? So the negative
Yes.
charge is getting decreased because of resonance, and that's why it's not the answer.
Okay, sir.
Okay. Fine. Next. Fine. So it's steric hindrance here in SN2 mechanism, right? Because tertiary halides are going to have the highest steric hindrance, so they'll have the least stability, least reactivity in SN2. Next. Which of the following is the correct order of decreasing SN2 reactivity? Now, decreasing means the primary will have the maximum reactivity, that is RCH2X, R2CH2X, and R3CX. Yes, directly we can say A is the answer, SN2 reaction. Okay. Right. How many questions are remaining? Okay, we are almost there. Okay. Right. Okay, mathematical form. I don't have to go through any of this. Right. Now next. The reaction AB follows first order kinetics. Reaction AB follows first order kinetics. The time taken for 0.8 moles of A to produce 0.6 moles of B is 1 hour. Right. What is the time taken for 0.9 moles of A to convert into 0.675 moles of B? Now the answer, the reaction is very simple. This thing. Right. So this is the first order reaction. Right. So A giving B. Now, initially what they're telling is that 0.8 moles of A is giving 0.6 moles of B. 0.8 I had initially, and at finally got at some time T, right? It is becoming 0.6. So what should have been the concentration here? 0.2 out of 0.8, 0.6 would have gone here, so remaining is 0.2. Now, when you go to your K, you have to find first, it is 2.303 by 1 hour. Right, 1 hour, or you can write 60 minutes or whatever you want to put, you put here into log of initial concentration of A is 0.8, right? Final concentration is 0.6, right? So first you'll find your K value. Once you find your K value, then what we can do? Again, you see A giving B. Initially we are starting with some 0.8. It is, oh man, initially how much we're starting with? Initially we're starting with 0.6. Now this time 0.6. Taken for point, I don't know, 1, okay, what a time taken first, 0.9 moles of A to become 0.675 moles of B. Okay, so in that case, we are starting with 0.9 moles of A, initially 0, final initially 0, and A becomes 0.67, sorry, B becomes 0.675, so this becomes 0.9 minus 0.675, that will be this will become 7, if I, 0.25. No. Yeah, 0.25 only, right? So this will be 10, this will be 16, so 9, 5, and this will be 2.295. Is it correct? No, sorry, this will become 9, right? 0.225. Okay, so this will become 0.225. That would have been the final concentration. Now you know the K value, substitute it now. First, I'll bring the K value here. Now you say 2.303 by T. T you have to calculate now. Log of what is the concentration now? Initially we had 0.9, now it is becoming 0.225. Find the T value. This is how you need to do it. Calculation I'm not showing you, you can easily do the calculation. It's very simple. Okay, and easily find the answer also. Okay, right? First you find the K value, substitute the K value in this and find the T value, but you have to be very careful. You have to substitute the concentration of A only. You know, you cannot take A and B together in this equation. Concentration of A by concentration of A at final concentration, final time. That's what you substitute here. Okay, right. Next, in the decomposition of A into product having K value of this much at 10 degrees Celsius, the energy of activation is this much. What would be the temperature? At what temperature K would be equal to this much? Now, direct formula substitution. Log of K2 by K1 will be equal to EA divided by 2.303 R into 1 by T1 minus 1 by T2. This is the value you substitute. Everything is given. T2 is what is asked. EA is given. R value is substitute as 8.314. K1, K2, everything is given. Right? I have to substitute everything and find the T2 value. Direct one of again, I'm not doing the calculation. You can easily do this. Not a big deal at all. Right? Okay. Next. Which one has the highest dipole moment? Okay. Now, guys, this is a very tricky question. All you have to understand is when you have CH, Cl, Cl, CH2, Cl2, and say when you have CH, Cl, 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 and when you have CCl4, right? Now remember that the chlorine atoms are very big, right? When the chlorine atoms are very big, what you have to understand is this lone pair and this lone pair on chlorine will try to repel each other, and these will go very far away from each other, right? These two chlorine atoms will suffer more repulsion, and everything actually, everything will try to suffer more repulsion. They'll try to be very far away from each other, right? So the more the amount of chlorine you have, more the bond angle you're going to have, right? And the thing is that the bond angle and your dipole moment are inversely proportional, right? Higher the bond angle, lesser will be the dipole moment. Okay, so keeping that in mind, we can conclude that this and this, they'll move around and making this bond angle shorter. And now in this case, there are 3 Cls, right? Though they will move so much apart, so that okay, now we're not about this angle. So you see that, so this angle will be lesser and this angle between them will be little higher, right? This will be lower. So this is going to have higher dipole moment. So CH2Cl2 should have a higher dipole moment. One will have the higher dipole moment, right? So the bond angle.
Sir.
Yeah.
Sir, but in CH2Cl2, like the Cl can also be in opposite sides, right?
No. You cannot say opposite, right? This is tetrahedral molecule. They'll not be in the same plane also. Right? This is sp3 hybridized carbon is tetrahedral. Right? Even if you put it on the opposite side, doesn't mean that they'll cancel out each other. Doesn't make sense, because you know how the tetrahedral structure looks. Wedge, dash, all those things will be there.
Okay, sir. Understood, sir.
Understood, right? Oh, next. An organic compound with molecular formula C8H8O forms an orange red precipitate with
Sir, I have a doubt, sir. In the previous question, in the CCl4, does it get cancelled out, sir, on both sides?
Yeah, CCl4 dipole moment is 0. Yes, absolutely.
Yes, sir. Okay.
Right? Okay. Next. So an organic compound A with molecular formula C8H8O gives an orange red precipitate 2,4 DNP. That means it is giving me 2,4 DNP test, right? So C double bond O is present, right? Second thing is it gives me yellow precipitate heating with iodine in the presence of sodium hydroxide. That is your iodoform test. So it is having C double bond O with one CH3 also. That's what we understand. It neither reduces tolerance nor reduces swellings. Definitely it is going to be a ketone. Another carbon atom is going to be there. Okay. And nor it decolorizes bromine water with Bayes reagent. Obviously, it does not have any double bond, triple bond also. That's what I understand. Decolorizes bromine water. On drastic oxidation chromic acid, it gives a carboxylic acid B with a molecular formula of C6H6O2. That's it, that's it, done. You have to have 8 carbon atoms, right? 8 carbon atoms with 8 hydrogen atoms. So you cannot think of a straight chain structure. All you can think of is benzene, because it is going to have C6H6. And you have to somehow make 2 more carbon atoms with making sure that there is a C double bond or CH3, and this is the molecule that I can make. Very, very simple. Okay, everything included. The molecular formula C8H8, you will have 5 here and 3 more coming from here, and 2 more carbon atoms and 1 oxygen atom. Very simple, right? Now, if I go for extreme oxidation of this is going to form C double bond O with a OH. That's it. This is your carboxylic acid. Benzoic acid is what is B. This is your B. And this is your A. Very simple. Okay. Anything else is there? Yeah. We are done. Right? Okay. Fine, people. We'll see you again next week. Thank you. Thank you so much. And any doubts anybody has? Yeah, tell me.
Sir, in the 20th question.
20th question. I don't know which is 20th question. The numbers are not given here. Can you tell me?
comparison between the concentration.
Concentrations, huh?
So that HCl, that molar mass was given.
Tell me, huh?
Sir, in that question, can we find the what is the molar mass of the given mass of the compound, and then can we find
No,
the,
Kana, given mass you cannot find out. All you can given mass also, if you find it, is not going to make any sense because number of moles, if you find out, and that's done, right? That is all we require for the calculation of new molarity, right? Number of moles would be equal to given molarity into the volume. It'll give the number of moles. Now find the new molarity because you know the number of moles. Now the volume is going to change. That's all you can do. Finding given mass does not make any sense there. Okay.
so finding the given mass and substituting in the next formula, won't it give the correct?
That yeah, answer you will get, but it's like touching the nose like this, touching the nose around your this thing. The easier
No,
method
but
is what
I
I
didn't
do.
get the answer, sir. I got it as 64.3.
No, Kana, you should be getting. So if you want to calculate the given mass, you have to calculate the number of moles first. Number of moles would be the molarity into volume into 10 to the power minus 3. Correct?
Yes, sir.
Right. And that number of moles into the molecular mass of HCl, that would be 36.5. Correct?
Yes, sir.
Right. So that will be the given mass. Now that given mass you take and go to the molecular molarity formula. Molarity formula is given mass by molecular mass. That mass, whatever you found out, divide by the molecular mass, that is 36.5. Correct?
Yes, sir.
Divided by the volume, that is new volume, 20 plus x. That will be equal to 0.2. You should be getting the answer.
Okay, sir.
Okay. Anybody else? Any other doubts? Okay, people. Thank you so much. We'll meet again.
Thank you, sir.
Thank you.